Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello everyone, and thank you for joining our webinar session today for the 2023 AI, ML and 5G Challenge hosted by the ITU, the International Telecommunication Union. My name is Mia Nisho and I have the honor of moderating today's session. The Machine Learning Challenge, now in its fourth year, aims to create a community to solve network-related problems using machine learning. The challenge this year will be featuring a batch of new problem statements, all relevant to the updates and progresses we've seen in both AI and communication networks. I'd like to briefly go over today's program. We'll first start off with two expert talks. I'd just like to point out that we do have a slight change in topic. The first talk will be on R&D activities for beyond 5G and 6G, and the second talk will delve into the revolutionary AI-based live video distribution technology used for realizing digital twins. Following these two talks, there will be an explanation of the two problem statements from Japan this year. KDDI will present a challenge centered around the development of a network classification model using the advanced NDT technology. We will then have an explanation on the problem statement from RISING on 3D location estimation using RSSI wireless LAN. I would also like to briefly introduce our experts who have kindly joined today's session. We will first have Professor Nakao from the University of Tokyo. He's a highly esteemed professor in the field of telecommunication, with his research lying across many relevant topics to do with 5G. Our next speaker will be expert Junichi Kawasaki, who is currently engaged in the network automation supported by AI/ML technology at KDDI Research. And then we will have Dr. Yusuke Shinohara, who is currently a lead research engineer at NEC. His research interests lie in QoS, control, and software-defined networking technologies. Last but not least, we will have Professor Koichi Adachi from the University of Electrocommunications. His research interests include cooperative communications and energy-efficient communication technologies. Before I pass over the floor, I would like to remind everyone that we are counting on you, the participants, to help create an engaging discussion. If you have any questions, please make sure to type them in the video wall and we will take them during the Q&A session right after the talk or if we have time in between. So over to you, Professor Nakao.
Okay, thank you very much, Mia, for a great introduction of myself. So today, do you see my slides?
Yes, we can.
Okay.
Thank you.
Okay. All right. So today I'm going to talk about R&D activities for beyond 5G and 6G, and especially about AI integration in the softwareized beyond 5G and 6G infrastructure. So I'm a professor at the School of Engineering, University of Tokyo, but at the same time, I'm chair of the International Committee of Beyond 5G Promotion Consortium of Japanese government. So I'd like to teach you what is Beyond 5G, because we are all working on Beyond 5G, 6G infrastructure. And right now we are using the 5G, and we started integrating AI already in the 5G infrastructure. And today I'm gonna talk a little bit about our Open RAN activity, especially RIC, RAN intelligent control stuff. And we are looking out for opportunity for integrating more further AI and machine learning into the mobile network infrastructure. So I did several webinars in the past. I have to show this because this is Japan's direction for key features for beyond 5G. And of course, we like to extend the feature of 5G mobile infrastructure, such as large capacity, low latency, and ultra numerous connectivity. but at the same time, ultra low power, ultra security, and autonomy and scalability. So which are expected to add new features contributing to generate the sustainable and new values in the society. So I'd like to stress we are currently focusing on the autonomy, autonomous coordination among devices without manual intervention, and also construction of optimized network, highly integrated wire and wireless networking. So, so I'm, as I said in the beginning, so I'm wearing the hat of international committee chair. And recently we established this Open RAN subcommittee between, so this is co-organized by a planning and strategy committee and international committee. So this activity is both strategically important and also internationally, we need coordination to define this Open RAN specification. So other part, you can safely ignore. If you have time, you can check out all these organizations collaborating with the Beyond 5G Promotion Consortium. But international committee, we are trying to grasp the international trends for the promotion of Beyond 5G and try to identify the strong partners to work with. So this is the mission of international committee, but especially I'd like to focus today on Open RAN subcommittee activities. So as you may all know, Open RAN, especially, so the very concrete specific activities led by NTT Docomo and all these mobile carriers all around the world. So we have open interface defined among the various mobile infrastructure components, such as radio unit, central unit, distributed unit, and also the cloud combined with cloud, so we can define the interface to the cloud too. So the left picture shows the closed network, and we treat all these mobile network equipment as a black boxes. But now we would like to open the interface between these components and allows multiple vendors with vendor devices to interconnect. So for example, if you like to use a specific vendor's RU, so then you can do that because there is clearly defined open interface between the RU and the CDU. So in the same way, we can define an open interfaces among all these components, and so that you can switch among all these multiple vendor devices if you like specific ones. So this is very important to create a safe supply chain and also create a new ecosystem, because we can invite, for example, startup companies which are specialized in developing a very advanced RU only. So you don't have to develop the whole mobile infrastructure by just a single vendor, but instead you can be specialized in some component, and then you can create a new market for this specific vendor. So recently, so we I'm now wearing the hat of the University of Tokyo, but so we are, lots of university people are now engaged in ORAN activities. So this in particular ORAN workshop was held in Osaka, and so this one is ORAN for Vertical Industry Workshop, which was held in Osaka in June 2023, recently, and I gave a keynote here. My talk title was Towards Open, Flexibly Programmable, and Rapidly Deployable Cyber Infrastructure. And I think there will be a recorded video. So I'm trying to deliver a very similar talk today, because this is very important for us. especially from the AI integration standpoint. So before talking about the RAN intelligent controller, I'd like to introduce what we have been discussing in the subcommittee of Open RAN in Beyond 5G Promotion Consortium. So this is a slide from NEC, and they expect for global 5G business, they aim for 20% market share in the Open RAN market into 2030s. So this is a very aggressive goal, but they believe in this goal, they can achieve that because, as I said, it opens up, it can achieve the safe supply chain, and like they can open up new opportunities for a new ecosystem. So, and this is a slide from Rakuten Mobile, and they have a Rakuten Symphony, a new company, which exports their softwareized infrastructure to all over the world. And the existing customer number is still small, but the potential customer, if you can see, this red circle. So in total, they are approaching 123 companies to export their softwareized infrastructure to. And you can see that not just the Asia Pacific, but can export their systems to Europe and North and South America. Okay, so but there's not only good things about Open RAN, but also challenges that you need to solve, because so this open interface is still under development. So if we like to connect all these mobile equipment components together, so we have to have testing and integration facility. So Japan is recently trying to establish this OTIC, which is all-round testing and integration center at several places, but now the first one was established in Yokosuka area. So it's called the Japan OTIC. So this is jointly organized by NTT Docomo and KDDI and Rakuten Mobile and SoftBank. All these 4 carriers, telecommunication carriers in Japan. So we just started this activity, but recently we had a lecture for what is ORAN and what is the OTIC's objectives. And also we open this verification system that you can bring in your own equipment, and then testing against all these other components, and put them together to work as the single mobile infrastructure system. So another group, this is a slide from PRV, and they are offering this test and integration equipment, and also they are leading this focus group, TIFG, for testing in OTIC. And another slide from Rakuten. So they would like to not just the ORAN, but they are working on fully virtualized cloud native network. So cost advantage, they figure this is very much, it's like a 30 to 40% of cost saving by Rakuten Symphony. So it's not just by the open ORAN activity, but they're working on a vRAN, virtualized RAN system. And you can see that network optimization by AI. So they are already forecasting this AI should be integrated in the softwareized mobile systems. So this is probably a very interesting activity, commercial activity done by KDDI and Samsung and Fujitsu. So they have traditional RAN operated recently, but we see that they are working on an open RAN equipment already deployed. So this is not just the ORAN compliant, but also the equipment is virtualized. So this is the first open virtualized 5G base station commercially deployed by KDDI Corporation. So if you can see this picture, so this is actually an instance of the vRAN mobile infrastructure. Okay, let me briefly talk about ORAN architecture. This is the overview picture of ORAN architecture. And I have been talking about ORU. So this is RU unit, ORAN compliant, and DU distributed unit on top of that. And also here's an OCU, central unit component. But you may notice that on top of all these components, they are RIC. So this is RAN intelligent controller. So this is where the AI comes into play. And we can implement intelligent RAN controller in this layer. And there is a control interface defined already. And there are two RIC components here, the non-real-time and the near real-time. So this is based on okay, so the left picture is a little bit detailed diagram, but the right one is simplified. Maybe you can take a look at this right one. So as I said, near real-time RIC and the non-real-time RIC are located. And so we usually call it X app and R app. If you want to implement application here, so then application will be implemented in this layer. So near real time means that we have a control loop less than the 1 second period. And also control loop is if control loop is longer than the 1 second, so then we're calling it the non-real time. So based, depending on what kind of application, AI application that you like to run to control run intelligently, we can use this specification to implement or try out your own idea about AI integration to the mobile network infrastructure. So this is a slide that NTT Docomo's published recently. So this is just one scenario, but this is the data flow of the, if you want to apply AI into the data that you're collecting. So there is a data collection and data preparation and AI ML training and AI ML model management, and going to AI ML inference that is working onto this near real-time RIC. So this scenario is just a very simple formulation of how we can implement or integrate ML into this mobile infrastructure. So due to the time constraint, I'm not gonna introduce all the scenarios that they defined, but if you are interested, you can read this document on the web. It's open to public. You can check out what kind of scenarios that you can define in this architecture. So, we are just started working on these RIC applications, but I think you can take a look at the ORAN activities and possible applications that I could identify from this AI ML integration examples. So the first one is traffic steering. So for example, if you like to do a resource management of the radio resources, RLM, radio resource management by RIC, and also application traffic provisioning. I think my students are working on in this area, application traffic provisioning, which is very, very interesting activity for the people who are working on the network slicing. Also, some commercial companies are working on the power management. So if a UE is not around in a base station, maybe you can intelligently turn off the base station power. And also UE resource usage prediction by AI can solve this power management problem very nicely. In terms of resilience, we can do all sorts of traditional work like anomaly detection, disruption prediction, and congestion mitigation. But this is not going to be a point solution or custom solution, but we can clearly define in the framework of Open RAN, ORAN RIC architecture. So the last one, dynamic spectrum sharing. This is very interesting because we are limited by the spectrum. So there is activity that we like to control dynamically, the sharing of the spectrum dynamically. So which is also done intelligently by this RIC, the RAN intelligent controller. So there are more and more applications coming from this community, and we are very interested in watching, what kind of new applications are enabled by AI integrated in the RAN system. So, let me, introduce a little bit about what kind of research activities that we are doing. So last time, I introduced the local 5G regulation instated in Japan. So local 5G enable establishment of customized networks with flexible specifications, and also the establishment of 5G systems prior to area coverage by mobile carriers. Because we can apply for the license band, we as non-telcos can apply for a license of local 5G, and we can operate our own local 5G system. So there are lots of interesting local regional challenges that you can solve by this local 5G system. We are observing that the 5G systems are not deployed very rapidly these days because of the COVID situation, and also the infrastructure is very costly, so it takes time for telcos to deploy their own public 5G network. But instead of waiting for their deployment, we can start our own deployment by local 5G. So this is the idea. And we can also integrate the ORAN system in it. And also we can, also do RIC applications also. So sort of, say that we are democratizing 5G by local 5G. So this is the picture of our plug fest. We can bring in our own local 5G equipment and try to do an interoperability test. And if you look at this picture, we can operate our own cloud local mobile. So right now we are doing the plug fest for equipment itself, but in the end we can run application integration and especially AI ML integration also. Most of them are softwareized, and this particular base station that we developed recently, this is a softwareized portable local 5G boxes. And still, if it is if it is softwareized, people are worried about the performance, but still you can achieve almost 940 megabps downlink speed and uplink 140 megabps speed. So this particular base station can do 4 layers MIMO and 1 watt per channel. And there are 4 channels, so we can achieve 4 watt, which is good enough to cover the area of the local 5G. And we recently, devoting ourselves to developing a new small SDR, software-defined radio board, so that you can do a softwareized base station. This one is an M.2 size, and particularly, in that specification, this stick is 80 millimeter by 22 millimeter wide and 5 millimeter thickness, and this is fairly small one, but we can use this for develop the 5G base station. So this is a little bit less performance version of our base station, which can do a 2-layer MIMO, but it's a low power. And we can still do a 1 watt per channel. So in total, we can achieve 2 watt, and performance is a little bit less. So it's can achieve 650 something downlink speed. But this is small and also low power. So if you like to have a small form factor and a low power, and that can be quickly installed outdoor, so then you can pick up this unit. So we recently started selling this unit at our startup company, and Flare Systems started selling this unit. And we did the field test. So with 4 watt with a sector antenna, we can achieve coverage of about 1 kilometer from the space station. It's beam formed, so it's not like a omnidirectional. So this is custom, this base station is customized, in terms of a TDD pattern. So uplink and downlink ratio can be changed by software. So if we set downlink to uplink to 7 versus 2 slots, so then we can achieve downlink about, almost about a 900 megabps, as I can show you. And if you change this to TDD pattern to 2 versus 6, so then we can achieve like 17 megabps, so which is marvelous number of uplink speed. So this customization can be done, and also we haven't done that yet, but we can modify the space station because it's a softwareized. We can integrate AI and ML functionality in it. So, and also mobile edge computing can be done within this unit. With this unit, we like to do local 6G. So we like to bring power to the general people, not only telcos and network vendors. We are university people and local governors, and also regular people can define their own local 6G and also try to solve these local government problems. So the example can be countless. So we can work on this by democratization. Okay, in summary, so I introduced this Open RAN, softwareization, spectrum sharing. So formation of synergies in technological and institutional direction through like-minded country cooperation and intergovernmental collaboration is very important. And as I said, local 6G type of interesting activity, international dissemination and partner formation of advanced technology and their values. So this is also important for international collaboration. So I don't talk about protocols today, but early uptake of global advanced users in various regions and various countries is also important. Japan may have very advanced users, maybe if network vendors, network carriers are looking for advanced users in particular country. So then we can take advantage of international collaborations. Also, AI, semiconductor, quantum are now all related. So enhancing national strength through the development of cyber infrastructure through cross-sectoral collaboration among various fields, that's also important. And finally, but most importantly, international cultivation of distinct human resources is very important. And through these webinars, we can work on all together and develop human resources for especially younger generations. Thank you very much for your attention. This is the end of my talk. Giving back to Mia.
Thank you very much for your talk, Professor Nako, especially how the idea of local 5G is democratizing 5G quite appealing. And I think we can all agree and understand how the importance of international cooperation to realize these goals. We just do have 2 questions for you from the audience. On slide 13, Neda is asking, do we use high processing GPUs to process the packet? If you just answer that question in a minute or 2, and then we've got another question as well.
Okay. Okay, we could use GPUs there for process packets, but not necessarily. So, we can, well, in fact, we can use all kinds of computational components there, but especially for a deep neural network, type of application require very high processing power. So then people tend to use GPUs also. But not necessarily it's GPU, but also regular general purpose CPU can be used for processing packets also. Well, it depends on the application that we want to achieve.
Okay, thank you very much. And then on slide 44.
44.
The question is, what is the range of these 5G custom nodes? Do we manage the interchannel interferences?
Okay. 23. Okay.
Oh, 23.
Or 22 or 22. Okay, I don't know which one is that. So if you can speak up, you can just ask questions, but
that's not possible, unfortunately.
okay. All right, I can guess. So interchannel interferences. Well, if you're talking about these pictures, so there are various kind of applications running, all around, the single base station. So the one idea is that you can introduce a network slicing to differentiate QoS among all these different kind of applications. But if you're talking about the wireless, interference, so then, local 5G base station, if you would like to deploy and get a license for this particular license band, so this license band is dedicated for a local 5G system, but it's next to a commercial public 5G frequency band. So you like to be very, very careful not to interfere with the public 5G frequency band. So this is one of the stringent requirement from the government to get a local 5G base station.
Thank you very much. And thank you very much for the interesting talk. I'd like to next call Dr. Yusuke Shinohara to turn on your camera and share your screen.
Okay. Can you see my face? Oh, just wait. Okay.
I can see your screen.
Okay. Thank you for introducing me, Nishio-san. And hello, everyone. I am Yusuke Shinohara, a researcher in NEC. Title of today's my talk is Remote Monitoring System Using Video Streaming Control for Image Recognition. My topic is organized at the important point of video streaming control technology as a vision and our video streaming control technology for image recognition and its application to the real world remote monitoring system for self-driving buses as demonstration experiment. Okay, let me start my presentation. First of all, I'm going to explain our vision, requirements of ICT platform for digital twin as background of our research. Okay, this is the background of our research. The need for digital transformation is increasing, and IT and network is becoming more important as an infrastructure to realize digital transformation and its enabler, digital twin, focusing on external environment. Labor shortage and such kind of social problems are getting more serious. On the other hand, the importance of IT and network platform is increasing, as I said, for business process re-engineering by digital transformation. Okay, in such a situation, our vision is to enable an intelligent IT and network integrated platform to provide higher application performance for digital transformation. Examples of DX applications include remote control of construction equipment, remote management of AGV in factories, and remote work monitoring and remote management of self-driving buses. In promoting digital transformation utilizing wireless network like local 5G, we will be able to show its superiority by providing application and infrastructure assets vertically. Okay, to achieve IT and network platform, we should solve the issue for the application performance. We think that the important point that is a key performance indicator is not only basic ICT platform performance, it is QoS, but application performance, it is QoE. Moreover, in digital transformation era, the important performance is not for human, but for AI. Considering video streaming application, key performance indicator for human is waiting time. However, key performance indicator for AI is recognition accuracy of image recognition AI. So we should solve the issues QoS requirement estimation and for the application and control to adapt to varying QoS requirement of application. Okay, next, I'm going to explain our technology based on our vision, video streaming controller for image recognition. Okay, this is the background again. Real-time video streaming applications are widely used to monitor remote sites for surveillance. One example is a video surveillance system connecting monitoring servers and cameras installed on cars over a wireless network to monitor the real-time situation of cars. On the other hand, with the recent explosive technical progress of DNN or such kind of AI, video surveillance is increasingly being performed not by humans but by computer vision systems. Conventional encoding methods such as H.265 are designed to reduce the video data size while keeping the same human perceptual quality, and perceptual mechanism of computer vision is quite different from that of human. So we need the video compression method for our computer vision system. Okay, the key problem of video streaming, the network resource of wireless network will be insufficient. In this situation, high bitrate video could not be transmitted. Black noise occurs, and it causes image recognition errors. To solve the problem, our technology selects region of interest (ROI) and improves video quality of only ROIs. It can seriously reduce video bitrate while keeping image recognition accuracy. In this slide, I'm going to explain the strategy to use the ROI. Okay, to explain that, I'm going to explain the method of the object detection in the image by current major computer vision method, CNN. Most object detection methods uses only the feature information extracted from pixels in and around the object. Convolutional layer is a core of CNN. In the convolutional layer, the image becomes abstracted to a feature map. It uses a set of runnable filters to extract feature information. Next, local or global pooling layers to streamline the underlying computation. Pooling layers reduce the dimensions of the data by combining the output of neuron clusters at one layer into a single neuron in the next layer. Local pooling combines small clusters, typically 2 by 2. Okay. And finally, free connected layers connect every neuron in one layer to every neuron in another layer. It is in principle the same as the traditional multi-layer perception neural network. The flattened matrix goes through a free connected layer to classify the images. Okay, next we propose the method to compress video for computer vision system. In this talk, we focus on the object detection and assume the system to compress the encode video on the sender side. On the receiver side, decoder decodes images and the image recognition models processes the images. To achieve the efficient compression, we specialize video quality control for the target image recognition model. Considering the feature of image recognition, we adopt the strategy to detect ROI and assign low image quality to outside ROI. Outside ROI doesn't affect recognition performance. Moreover, to achieve efficient compression, we control image quality inside of ROI. On the receiver side, decode video and recognize images by the image recognition. Okay, next, we control, this is the method to control image quality inside ROI. To control the image quality inside ROI, we run the estimate confidence score by the target image recognition model for each image quality to estimate required image quality. In the running stage, we detect the object and running data with the target image recognition model and compress the object image in predefined image quality. Then we detect or recognize with the target recognition model and compress object image and get the confidence score to judge the objects are recognized or not in the image quality. We run the score by confidence score estimation engine. It is binary classification computational neural network. By running score, we can take advantage of the neural network technique, such kind of knowledge distribution. Finally, in the estimate stage, our confidence score estimation engine estimates the confidence score of the object image in each image quality. Okay, next, we evaluated the image quality control and encoding performance of our proposed method with driving dataset in offline environment. We used Kitty dataset, which is famous in driving dataset. We also used CentiNet as the target object detection model, single shot detector as the detection to detect ROIs. And finally, we used mobile network v2 based network as the confidence score estimation model. Okay, these graphs show the results comparing with the standard H.265 in 6 scenarios in terms of data size and recognition accuracy of the target recognition image recognition model. Note that we obtained data size by dividing data size compressed with the method by base data size that is compressed with the standard H.265. From these figures, H.265 resulted in significantly low recognition performance because it is designed to reduce the video data size while keeping the not the same machine recognition quality, but the same human perceptual quality. On the other hand, our proposed method outperforms the standard method. Our proposed method could reduce 18 or 95% data size, even though it shows better recognition rate than H.265. Because our proposed method not only compressing image outside RI with lowest image quality, but also compressing image inside ROI with optimal image quality by estimating the detection score of the target image recognition model. Okay, this is a simple experimental evaluation, remote monitoring for cars. The image recognition, object detection, and range detection and the depth estimation are used to support remote monitoring. Left side shows the video streaming with existing technology, and the average bitrate is 5 megabps. On the other hand, right side shows the video streaming with our technology. Our technology reduces bitrate by 1/10 while keeping the accuracy of image recognition. This technology will be useful for the remote monitoring. Okay. The next, I'm going to explain the result of demonstration experiment of the application of our technology. We applied our technology to remote monitoring system for self-driving buses. Okay, this is the background of the experimentation. Autonomous driving bus is attracting attention to maintain transportation service in rural areas. The number of passengers of buses is decreasing in rural areas, and most of bus companies in red in rural areas. It is difficult business environment for bus companies. They need to cut costs. Okay, self-driving buses are attracting technology to improve their profit. However, the self-driving technology is not perfect now, and the level of level 3 and level 4 is the levels for the time being. Self-driving of levels needs human these levels needs human assistance, and remote monitoring is needed to achieve the self-driving buses. Okay, this is the requirement of remote monitoring of self-driving buses. The key point is that the one operator needs to monitor and control multiple buses at the same time. At the left side, this graph shows the breaking down of the cost of fixed route buses. More than half is labor cost, so enabling an operator to to monitor multiple buses is necessary to reduce the cost. Okay. Okay, to solve the issues, we developed the remote monitoring system based on our video streaming technology for image recognition. Our system alerts notification based on the image recognition, such as object detection, lane detection, and this depth estimation to enable an operator to monitor multiple buses. That is necessary to reduce the cost. Okay, this is the monitoring. This is a detail of our monitoring system to enable an operator to monitor multiple buses. The system has two monitors: integrated monitor and detailed monitor. Integrated monitor shows multiple self-driving buses, and detailed monitor focusing single bus that should be monitored. A focusing bus of detailed monitor is automatically switched based on alert from image recognition. So image recognition accuracy is important, and also QoS control concerning the accuracy is important. Okay, with the technology and systems, we demonstrated the effectiveness of our technology and systems. We used two self-driving buses on public road in Japan. Each bus equipped 4 cameras to monitor the situation of the bus in remote monitoring center. Okay, we demonstrated the, this is the running route, round trip, Maebashi station, Maebashi station to Chuo Maebashi station, and about 20 minutes and 2 kilometers. This is self-running, self-driving buses running on public road, and this is the remote monitoring center. Okay, this is the system setup of our experimental demonstration. We used local 5G around the Chuo Maebashi station. There is complicated intersection, and we should monitor there. In other area, we used LTE network to send video streaming data of 2 self-driving buses. In the monitoring center, watchman monitors the situation of these self-driving buses through monitoring system. Okay, we evaluated our, first of all, we evaluated our video streaming method for image recognition. Left side shows the video streaming with existing technology, and the average bit rate is 5 megabps. On the other hand, right side shows the video streaming with our technology. Our technology reduced the bit rate by 1/10 while keeping the accuracy of image recognition. the technology will be useful for the remote monitoring of several buses. Okay, and we also evaluated our monitoring system. We confirmed detection of checkpoints to be alerted and recognizable situation by alert on checkpoints. We also confirmed that it is easy to monitor two self-driving buses by using our remote monitoring system. We interviewed to watchman and get good answer to achieve more monitor multiple buses. Okay, finally, I'm going to conclude my presentation. Our vision as background, QoE is key performance indicator of ICT platform for achieve digital twin and digital transformation. Based on the vision, we developed the video stream control technology for image recognition. We evaluated technology for remote monitoring system for self-driving buses. Future works includes automatic learning technology to apply various monitoring use cases. Thank you for the attention. That's it.
Thank you very much for your talk, Dr. Shinohara. We just have 2 questions in the chat. The first one is, can we utilize network social fairness instead of QoE to optimize the network placement utilizing digital twins? If you'd like to look, you can look at the QA in the chat as well.
Can we utilize network social? This is important issues, but okay. Currently, I don't have good answer, but it is important. Thank you very much. I'm sorry. I don't know. I don't know currently answer the question, but this is important view to solve the QoS problem issues.
Okay. We're just pushing in time, so we'll take the second question afterwards and the third question afterwards after the entire session is done. I'd like to next move on to expert Junichi Kawasaki to explain the problem statement from KDDI. Kawasaki-san, you're still muted.
Okay, can you see my screen?
Yes, we can see your screen.
Okay, thank you for kind interaction. My name is Junichi Kawasaki from KDDI, and today I would like to talk about our problem statement network failure classification model using network digital twin. So first of all, I would like to start with the background of our problem statement. A couple of years have passed since mobile network operators launched 5G services. 5G services, as you know, contain 3 main features: eMBB for high bandwidth, URLLC for low latency communication, and MMTC for massive communication. When operators integrate these features in 5G equipment, in their production network, actually it is a bit hard to satisfy all these features for all the networks at the same time. So network slicing, one of the key features in 5G, enables to provide suitable logical networks that satisfy each SLA. For example, URLLC slice for connected cars or EMBB slice for live streaming services. And slicing is realized by virtualization technology such as VNF and CNF that enhances flexibility of networks. While these advantages are added in 5G networks, the challenge here is how to maintain these networks that is more complex with a greater number of components than 3G or 4G. Recently, IMT 2030 document was published where this hexagon figure is presented. It shows the usage scenario of IMT 2030 or beyond 5G. The three features of 5G, EMBB, URLLC, and MTC, and extend each capability in this figure. In addition, sensing, AI, and ubiquitous are introduced as a new aspect here. The variety of features is expanded, so operators also need to establish networks by combining required feature for respective scenario in 6G. So I think the same challenge will remain. That is, how to establish resilient networks against failures or disasters. This is an important point. One of the expected solutions is network digital twin. Network digital twin, or NDT, is a virtual replica for a real network for supporting actual operation in a real environment. A general workflow of using NDT is like this. First, collect network information from a real environment, such as performance and technology information. Then, perform a variety of practical simulations on NDT. For example, upgrading device software or disaster recovery procedures. Finally, feedback to support operational tasks on a real environment by interacting with human operators or directly controlling network devices. The discussions on this topic has just started in several standard organizations. For example, in IRTF document, these use cases are explained, like human training, machine learning training, DevOps-oriented certification, and network fuzzing. This is a kind of testing for checking software reliability and network inventory management. Let's focus on the use case machine learning training. This is a description in the IRTF document. Here says that digital twin networks specifies the complete ML lifecycle development by providing a realistic environment, including network topologies, to generate the data required in a well-aligned context. And this figure presents the workflow of ML training on network digital twin. It consists of data collection from NDT, pre-processing, training, and then deployment on the real production network. The IRTF description in the previous slide mentions these steps surrounded in orange line. Here, it generates dataset for ML training on the network digital twin with a realistic environment. And here we have two concerns on network digital twin. The first one is it is hard to prepare the completely same network, since network operators manage total thousands or more network devices connecting each other. So it is not realistic to copy completely same network even in a virtual environment. Another one is the difficulties on simulating all the possible patterns in NDT. This is related to the first problem. Even only for one failure case, the simulation should be repeated more than 1,000 times to cover all the patterns. Considering that there are more than 100 failure cases in our network, I think this is also not practical to try to cover all cases to obtain sufficient datasets for ML training. If there are some difference of topology or simulation patterns between NDT and the real network, ML models trained on the NDT cannot be applied as it is. Therefore, the approach to create ML models from NDT data in these steps in a dashed orange line should be somehow refined to obtain good models for supporting the actual network operation. Based on this background and challenge, the purpose of our problem statement is to create a good ML model using the dataset generated in network digital twin that contains some difference with real environment. The objective of model here is network failure classification, that is root cause analysis, called RCA. We have set domain A equivalent to network digital twin environment and domain C equivalent to the real environment. Please note that this is the initial stage of network digital twin activities, so both of the two domains are prepared actually in our lab testbed and not related to the actual production network. In this problem, we provide three types of datasets: training data from NDT, training data from real, and test data from real. The procedure to create model is like this. Firstly, train models on training data collected from NDT and training data from real. There are only a few failure cases that occurs in the actual real environment, so the volume of domain C training data is small, and that of domain A is relatively large. After training models, evaluate the trained model with test data from real. The goal here is to develop a good failure classification model in terms of F1 score. From this slide, I will explain the details of our problem statement, including environment, test scenario, dataset, and task. So this is an environment that we used for this activity. We prepared a virtual infrastructure using OpenStack. Then we set two VNF-based 5G mobile core networks. The left one is domain A mobile core for network digital twin, and the right one is domain C for the real environment. Both domains have the same topology containing NRF, AUSF, MF, SMF, and UDM as C-plane node, and G-node B and UPF for U-plane node. The DN is data network connecting to the internet side. UE simulator is connected to AMF and G-node B for simulating UE or like a 5G smartphones registration and deregistration. In our problem setting, this UE simulator generates different trend of calls between domain A and C. For the system side, there are two functional components interacting with this network environment. One is failure injection that intentionally causes failures on the 5G cores. We use Ansible here to manage multiple types of injections efficiently. Another component is data collection that periodically obtains network information from 5G cores and stores it. The 5G core VNF software that we installed in this environment was Linux-based, so we use Linux command to get performance information of each VNF, such as traffic volume and CPU and memory usage. The next one is a test scenario for generating training dataset. At first, the UE simulator repeats UE registration and deregistration. It generates this generates a kind of background signaling traffic on C plane that can be measured in performance data. During this registration and deregistration cycle, the failure injection function repeats injecting failures and recovering from it to generating datasets. In the meanwhile, the data collection function keep collecting performance data and store. As for failure event type, we target on networking and computing failures on C-plane nodes. There are 5 types. The failure types are bridge down, interface down, packet loss, memory stress, and CPU overload. The characters in brackets here presents the actual name in CSV dataset. And the target of failure point are AMF, ASF, and UDM in this problem. And here, scenario for domain A and scenario for domain C includes the same failure event type with the same occurrence rate. But since there are a few number of failures in the actual real environment, we set the total number of failure injections in domain C scenario is smaller than that in domain A scenario. We obtain the dataset from the collected data during a test scenario. For this problem, we provide 2 training datasets in CSV format, training data A.csv from domain A that includes 80 samples per failure label, and training data C.csv from domain C, including 10 samples. For testing, test data C.csv is provided. These 3 CSV data have the same format like this, containing time, domain, label, and metrics information. I will explain each information in detail. The first one is time. The time information is presented according to this format: start time of event, dash, number, underscore, data collection time. The start time of event is a time when the failure injection event starts, as is shown on the figure below. The number actually shows how many times event has been injected since the test scenario starts. The data collection time is the time when the performance data is collected. Actually, the data collection derives data from networks periodically every 10 seconds in our environment. So there are multiple collection points, as you can see in the diagram, but we only use one collection point considering network convergence time after failure injection. Regarding label information for failure classification, there are mainly 2 types. First one is normal case, and the second is failure case. For normal case, there's no option here, so the label is normal. And for failure case, as I explained before, there are 2 elements: failure type that specifies what kind of failure was injected, and failure point specifying where the failure was injected. And the label name is presented in this format: failure point underscore failure type. For example, if the data is collected when interface down failure is injected on the ENS5 interface of AMF node, the label is AMFX1 underscore ENS5 underscore interface down. In another case of injecting VCPU overload on UDM, the label should be UDMX1 underscore VCPU overload start. And there are 5 failure types with 3 failure occurrence points. So total 16 labels are contained in all datasets, including normal case. The last part is metric. This is a main part of dataset in terms of machine learning. The naming rule of each metric is instance name underscore interface name underscore metric name underscore value. The interface name is used only for interface-related metrics. And there are two main categories in metrics: interface that provides networking information, and memory and CPU that provides computing information. One example for interface type is MFX1 ENS3 statistics in octets value that presents the statistical data on incoming octets on the network interface ENS3 of AMF. Another example for memory CPU type is MFX1 memory stats use percent value. That means the data is a percentage of memory usage on the instance AMF. So I have explained the environment and the dataset generated there. So from now on, I will talk about task in our problem statement. The task is to create a network failure classification model using the dataset generated in network digital twin. I think the task itself is simple. Two training datasets from domain A and C are provided with one test dataset from domain C. The training data from domain A contains a large amount of failure data, but training on only this data cannot create high-performance model because of the difference in call trend between domain A and C. On the other hand, training with only domain C data also cannot achieve good result because there are only a few failure samples in this dataset. So I would like to ask participants to try to enhance model performance by using some pre-processing and training methods. In training phase, participants will train a failure classification model for domain C using the training data from domain A and the data from domain C. After training a model, participants will evaluate the failure classification performance with a test dataset. In evaluation, participants will create confusion matrix using the test data and then calculate F1 score for each level. So total 16 F1 scores should be obtained as a result. Of course, participants can calculate other evaluation index such as precision and recall. And please include both of the confusion matrix and F1 scores in the submission document. In addition, we set one advanced task here. In this task, participants try advanced problem by decreasing the volume of training data from domain C included in training data C.csv. Participants try to develop a good failure classification model for domain C using the training data from domain A and reduced training data from domain C. This case provides limited training data from the target domain C, so it is a more challenging task. In training, firstly, participants decrease the volume of training data from domain C data set. Then the original value is 10 samples per failure level, so the possible number of samples per failure level is between 1 and 9. The following flow is same as the normal task, I think. So participant will train using the dataset and then evaluate the trained model that provides both confusion matrix and F1 scores as a result. Finally, I would like to inform you the submission guideline. So please submit presentation file containing your solution, such as type of ML model and originality in pre-processing and training method, and also evaluation result, including confusion matrix and F1 score of all 16 levels. Participants can include multiple results that are obtained with different volume of domain C training data For example, including the result of first trial using all of the domain C training data, and the second result by using half of domain C training data. So that's all of my explanation of our problem statement. So thank you for listening. I hope many of attendees here register this problem, and I would have the interesting solutions on October. So thank you very much.
Thank you very much for explaining the problem statement from KDDI for this year. I'd like to take questions to do with the problem statement or at the very end. So I'd like to quickly move on to Professor Adachi to turn on his camera and explain the problem statement from RISING this year. Professor Adachi, could you please? Thank you.
Okay, sorry, please wait for a while. Okay, sorry for taking the time. Hello everyone, I'm Koichi Adachi from the UEC Japan. Today I'd like to talk about the 3D localization, location estimation using RSSI wireless LAN, which will be the problem statement for the ITU AI ML in 5G Challenge 2023. So this challenge is organized by RISING. What is RISING? It's a cross-field research association of super intelligent networking, which is a special ad hoc committee of the IAC Japan. As you can see here, the Professor Nakao from the University of Tokyo is the general chair of this RISING, and many professors and faculty members and also the researchers from the companies are joining this RISING. And this the purpose of the RISING is to introduce, discuss, and gather information on research of intelligent communication technologies and systems with artificial intelligence. So let me briefly explain the background of this problem statement. As you know that the demand for location information is becoming more and more important, and also almost like essential information for our daily life. And the reason for this popularity is due to the emergence of like SNS or AR and VR. For example, like for the SNS, the map applications, SNS, such as Google Map and Instagram, and now it's not a Twitter, but it's a X, are quite popular. And whenever you upload some information, you can also tag your location information, and you can share some information with the others and also your friends. And for AR and VR, based on the movement of you and also the direction of your which direction you are looking, and you can get some information, some video or some kind of information about buildings. So for this kind of information, for this kind of purpose, the location information are quite important recently. And to get the location information, the most popular and most essential way is mainstream of location for many years is the GPS, Global Positioning Systems. For localization of the GPS, more than 4 satellites are required in the sky. So if the number of the satellites that can be seen from the mobile terminals or receiver decreases, the accuracy of GPS localization significantly decreases. So whenever you move, you are in the open area, you can get a good location information, accurate location information. But once you're, for example, like behind the buildings or indoor, you cannot get accurate information because you cannot get the satellites enough to localize your location. So to overcome this kind of problem, the researchers have been working on the RSSI-aided localization using the radio wave. What do I mean by the RSSI-aided localization is that when you receive the signal from, for example, the base station or access point, you can get a received signal strength, RSS information, that indicates how strong the signal transmitted from the specific transmitter is obtained. For example, like when you use your mobile phone to receive the signal from the base station, you can get the RSSI of the base station 1 and the base station 2, base station 3. So based on using this information, there are two main approaches are considered for the localization. The first one is RSSI map-based localization, and the second one is a range-based localization. So for the RSSI map-based localization, firstly, system constructs the map of the RSSI information in, for example, like inside of some buildings or some location. Then when you move into that place, you get the RSSI information from the base station, multiple base stations. Then the system compares the observed RSSI with a pre-stored radio map for localization. By doing this one, you can get quite a good, accurate localization. But the problem is that we need to construct the map priorly, in advance. So there is some kind of a drawback. The second one is a range-based localization. For this one, you use the multiple base stations and use the received signals from the multiple base stations to calculate where you are based on the TOA, time of arrival, and time difference of arrival, for example, and also the received signal strengths. This system does not require any map-based, the construction of map or something. But important thing is that the accurate channel model is required between the transmitter and the receivers. And also the problem is that if there is a multipath fading channels, localization accuracy degrades significantly. So we need to overcome this kind of problem. Given this challenge aims to verify if the artificial intelligence or machine learning aided 3D localization utilizing RSSI can achieve a similar accuracy as the GPS localization. And this challenge aims to explore the possibility if the data-oriented localization can replace the model-based localization. We have been giving this problem in recent 2 years. 2 years ago, we provided this problem statement using this kind of a system measurement setup. 2 years ago, we deployed 4 access points within the measurement area, and all APs have a load communication link at each measurement point. So for example, like please wait. Sorry. Okay. So 2 years ago, each measurement point have loads communication link between each access points, like this one. And based on this measurement information, you localize the position using the machine learning or AI. And last year in the problem statements, similarly, we deployed the 4 access points within the measurement area. And some of the points, measurement point, have a loss link between each access point, and some of them do not have the loss communication. So it's a non-line of sight condition. And at each measurement point, the location information of the access point and the measurement points were obtained by the GPS. And also the RSSI were measured at each measurement point. And based on this measurement result, we we ask the participant to localize the measurement each point. And this year, we introduced a little bit different model that in the previous 2 years, we have the same height of the access point, but this year we will use another model that, as you can see from here, we have the similarly 4 access points, but their height are different. And the same as the last 2 years, RSSI was measured in several frequency. RSSI are measured at each measurement point, but also we have include multiple frequency bands information like a 2.4 gigahertz and also the 5 gigahertz frequency band. So we have the multiple information about the RSSI at each received point, measurement point. And also the data set indicates if that location measurement point is a loss environment or n-loss environment from each access point. So for this problem, we will provide this data set. The training data containing the following information will be provided to the participants. Firstly, information about access point. The access point SSID, latitude, longitude, and height difference, and indoor, outdoor, and the reference information. And also the information about the received data at each measurement point includes the sequence number of the signal transmitted from the access point, and the timestamp, and the latitude and longitude, SSID, and the channel and LSSI information. And also, we will provide the information about surrounding environment, the map information of the measurement area, and loss and loss condition of the communication link. And this is the evaluation process. Firstly, the participants develop program and tune AR/ML structure, localization algorithm, and the parameters using training data, and submit all required materials and localization information using the first test data set to the administrative office by 27th of October. And we will select the top ranking teams, 3 teams. And selected teams will perform localization based on the second test data set during the grand challenge finale. And how we evaluate the submission is that each team is requested to perform localization based on the test data set without the GPS information. And the top 3 teams are supposed to compete by using the second data set provided just before the final competition. And this is evaluation criteria. We have the 4 criteria. The first one is average localization error, and detail will be in the next slides. And the maximum localization error. This is the maximum value among all the localization errors calculated using equation 1 in the second next slide. And algorithm performance, including the computational complexity, required memory size, scalability, and something like that. And fourth is the future direction of improving the proposed algorithm technique. How you can improve this approach in the future, you need to explain. And this is the evaluation criteria, the average localization error, which is defined as RMC of the localization given by these equations. So based on this equation, we will calculate the localization error, and we ask the participants to calculate the localization error, and we will evaluate the performance based on this one. So if you have any question or inquiry, please contact this mailing address, and detailed information about the problem statement and evaluation criteria will be provided on the website of ITU AR/ML Challenge. So this is the end of my talk. Thank you for your attention.
Thank you very much for explaining the problem statement from RISING, Professor Adachi. I'm going to now pass on to Vishnu to moderate the Q&A session. So if you have any questions to do with either the first 2 expert talks or the problem statements, please send them in the chat now.
Okay, thank you very much, Mia. We can start with, there are some questions. First of all, thank you very much, colleagues, for the excellent talks. It was just very, very interesting and a lot of information. Neda is asking, is it possible to route data in the network based on packet size, volume, avoid collision congestion in the network, reduce load balancing processing requirement? I believe this is a very generic question. I believe this came in during either Nakao Sensei's presentation or the next one. But I believe this is a really generic question. I would rather, if Nakao Sensei is there, I can ask him. I can request him. Is Nakao Sensei here? Is he still here? Nakao
Yes,
Sensei, are you still here?
I'm here. I'm here.
Okay, very nice, very nice. Thank you so much. Thank you so much for staying back. Yeah, would you like to take this question about routing data based on packet size and volume to avoid collision congestion and to reduce load balancing processing requirement?
Is this a question for KDDI problem statement?
It came in first in the beginning of the talk. So I think this is a very generic question. It's not to do with the KDDI. I'm pretty sure.
Okay. So okay, so I can take this as a general question. Yes, of course. So we can. So one of my students' work is that to classify the application traffic based on the packet size and also a time series of data like on the packet length change over time. And so based on that, we can do network slicing. And so for that, I'm not sure what it means by network collision, but maybe we can slice the network. Slicing means that we can divide the network resources to avoid interference between an application and traffic flows. So this way, the first thing we need to classify the flows based on the characteristics that you can observe in the network. Example, the things that packet size you mentioned. And also we can further extend that you can define your own congestion control per application flows. So yeah, that complex thing can be done. And also about the load balancing processing, we can define, specific QoS requirements for particular application flow once you classify the application traffic into slices. So, so if it is for a generic question, I can answer that at the high level. But if you are interested in the specific questions, so you can search for papers. The title is like application identification, application specific network slicing. Those keywords can give you a bunch of papers that people publish, including us. So that might be answer to this question.
Thank you very much, Nakao Sensei. Thank you for the pointers as well. Thank you very much. Can I take the next question? Can we utilize existing telecom data set to train models, extract patterns, and then utilize network orchestrator? All right. So I believe this is about training models from digital twins and then using it for VNF placement application. So that's what I understand from the question about training models from digital twins and not what the application maybe not failure classification, but maybe a different application like a VNF placement. So that may be the question. So maybe this came in when Kawasaki-san was talking. So can I ask Kawasaki-san, Do you have a comment on, I know you talked about failure classification, but the question is about VNF placement. Have you studied such problems before? Is it applicable? The network digital twin scenarios can be used for such applications like VNF placement also, please. Kawasaki-san, if you have comments.
Okay. Actually, we have not tried on the application to the VNF-CNF placement. But as a general comment, I think that is one use case for network digital twin, I believe. And in this question, it says utilize the existing telecom dataset to train ML models. But I think that if we just use the existing dataset to optimize the placement, it's possible without digital twin, and the placement by using the existing dataset is a little bit limited. So in using digital twin, for example, we operators can perform the reinforcement learning on the network digital twin for placement. Actually, it's not impossible in the production networks. So that is one approach. And for our problem statement, the problem is there's not so many failure dataset in the production network. So in our use case, we use the network digital twin to generate the failure dataset. So that's my comment.
Thank you very much, Kawasaki-san. Yeah, that's a good comment. Yeah, thank you very much. There is a question for Adachi Sensei. Adachi Sensei, is supplementary data set permissible? Means that not what you have given. Maybe external participant has some data. Would you like them to use that data in addition to what you have given, what Rising is providing, or it's only they are only allowed to use the Rising provided data?
Okay, thank you for the question. We did expect to have this kind of question, but I think that the participants should work on the problem with the data set we provided. So it's not allowed to use the external data set, I think. And even using the external data set, the environment are totally different. So maybe it cannot improve the performance, I think.
That's a good point. Yeah, I think in our previous competitions, we have not really allowed external data sets because scoring becomes a little difficult in that case. Yeah, you're right. Thank you very much, Adachi Sensei. I think maybe if the participant gives you some pointers to the external data sets, you can take a look offline. That may be the way out of this. Thank you, Stephen, for that question. What is that question? NDT just generates, network digital twin just generates data or use it for decision making as well. So I believe this question maybe on network digital twins. So Kawasaki-san, do you use this data for, I mean, the digital twin is used for just generating data as a source simulator, or are there models running in it which take some decisions as well?
Thank you for question. Regarding network digital twin, in our problem statement, it just generates data, including the normal case and failure case. And after that, the participant will try to develop machine learning model for failure classification in our problem. So that is our problem statement.
Thank you very much. Yeah, thank you very much. There is, do we use larger wavelength for higher localization antennas, millimeter waves for lower height localization antennas? I believe that's for other sensei again. So maybe because of the height difference that other sensei talked about, the question is, do we use larger wavelength or shorter wavelength for localization antennas to efficient use of waves and better management of physical obstacles? Yeah, other sensei, do you have a comment?
Okay, do we have, is it larger? So I cannot catch the point of this question, to be honest.
Well, the
we use the
question,
higher,
I
yeah.
think the question
Yeah.
is that do you use different wavelengths at all in the data collection? Do you use only one
Okay.
frequency
Yeah.
or different frequencies?
Okay, thank you for support. Okay, we will not use the millimeter wave, but we will use the two wavelengths, two frequency bands, 2.4 and the 5.2 gigahertz. Maybe 5.2, yeah. So multiple frequency bands we will use. Is that enough? I hope.
In the data, do you have these frequency values, or it doesn't matter? Do you have them? Do you have them labeled with the frequency band, or?
Yeah, labeled with the different, yes, different levels we have.
Cool. Yeah.
This latest value is for the 2.4, and this latest size is for 5 gigahertz. Yeah, we have the
Great.
differentiation.
Great. Yeah. Thank you. There is a related question. Larger wavelength can skip obstacle. Okay. Yeah. Thank you, Neda. Yeah. Thank you for that clarification. Yeah. All right.
Yeah, right.
Is,
You are correct. Correction. Correct.
right. Yeah. Thank you, Neda, for that clarification. Duke is asking. I believe he's asking Kawasaki-san, no? Yeah, I think he's asking Kawasaki-san, according to you, is there any difference between network digital twin and an autonomous system? Okay, so yeah, I think that there are different things. Autonomous system actually has the control loop right there. But let me ask Kawasaki-san. Kawasaki-san, do you see a difference between network digital twin and a complete closed loop with autonomous systems?
Okay, I think Vishnu already answered a bit, but I agree with him, and it's a different thing. And in my understanding, the network digital twin is one approach to achieve autonomous system, and it should be including in that system. So in that case, that autonomous system use the digital twin simulation result to achieve the closed loop on the real network. That is a autonomous system, in my understanding.
That is my understanding as well. Yeah, thank you very much. Yeah, thank you, Kawasaki. There is a question on the challenge. Any restrictions related with handling of information and results related to this challenge? I believe that may be a question regarding maybe some kind of terms and conditions for handling the data. So maybe I should ask a little directly, Stephen. The data. So let me ask Adaj Sensei. Adaj Sensei, the data is available for everybody. I mean, publicly available. Is it somewhere uploaded and publicly available? First of all.
Okay, so data may be uploaded to the portal site of this challenge. And I believe that data is open to public. There is no restriction over the usage.
Thank you very much.
But sorry, I'm not so sure. But if there is, I'm not so sure. But if there is any restriction, we will provide the information with together with the data set.
No problem. No problem. Thank you very much. Yes, I think if there is something, please update on the website, and we are good. Can I ask you again the results which the participant generates? Can they publish it along with you? Can they publish it separately? Is there something which are there any restrictions on publishing the results, please? Adaj Sensei, do you have a comment on that?
Sorry, I missed the question. Sorry. Could you please?
The results which the participant generates, can they publish it along with you, or is there somewhere else where they can publish? Is there any restrictions on publishing the results?
No, there is no restriction.
Okay. Can I ask KDDI? Can I ask Kawasaki-san same question? Is the data publicly available? Are there some conditions for use of data? Maybe the same question with the results, Kawasaki-san, please.
It's for KDDI problem statement. It's same as the rising one. No restriction basically.
Thank you very much. That's wonderful. Thank you very much, Kawasaki-san and Adaj Sensei, for that clarification. And thank you, Stephen, for that question. So that I think that's the end of published set of questions. And Mia is here. So yeah, thank you very much, everybody, for patiently answering the questions. And back to you, Mia.
Thank you very much, Vishnu, for moderating the final Q&A session. Thank you all participants for sparing your valuable time today to join the session. I would especially like to thank all of our speakers for giving incredibly valuable and interesting talks, as well as explaining in detail the problem statement for this year. Please note that the problem statement for KDDI is open from today for registration and participation. The link for registration should be posted in the chat soon enough, so you can start working on your solutions and submit the results in the portal. As mentioned in the very beginning, the information for our Rising problem statement will be uploaded soon, so please make sure to check the ITU platform for more updates. We are very much looking forward to your participation in these two problem statements from Japan. As for the AI and 5G challenge, we do have more interesting sessions planned in the near future, so please check the AI for Good program page for more details. You can also interact with us and other participants on the Challenge Slack channel, so we look forward to seeing you there. Thank you very much again for joining today's session, and I hope you all have a lovely day. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.